This is a flow field, one of the most unique and instantly recognizable creative coding effects. The advantage of writing our own code without any frameworks or libraries is that we understand how everything works. We can control it easily and we can do whatever we want with it. Let me show you how to make this effect flow around text like this by using built-in getImageData method. When you understand how to handle pixel data with JavaScript, you can do hundreds of complex and beautiful creative coding effects. In the extended class, I will also show you how to make the flow follow image shapes, preserve the original colors of the image, and handle animated transitions between two different colors. This is the second and final part of this series. Check out the video description for all related content. Down here on the main effect class, we have the init method. It splits canvas into a grid and creates angle values using this trigonometry formula. I still want to split canvas into a grid first. Then, instead of this algorithm, I want to draw text on canvas and calculate angle values of the vector field grid from there. Let's draw that text first. For clarity, I will put that code in a separate method. I will call it drawText. I will need access to CTX context object from here so that I can set canvas properties from here. At first, I will just pull CTX variable directly from line 2. We will refactor this in a minute. From there, I access font property and I set it to 500 pixels impact. I want large bold letters. Then I call built-in fillText method, which expects at least 3 arguments: the text to draw, and x and y coordinates where to draw it. The text I want to draw is JS, because we are learning about JavaScript today. Horizontal coordinate will be this.width, the width of canvas times 0.5, the middle of canvas horizontally. Vertical y coordinate will be this.height times 0.5, the middle of canvas vertically. As you can see, I'm pulling CTX variable from line 2 directly inside my class. I want to follow good practices and keep our classes self-contained, so I will refactor this. I will need access to CTX from drawText method as well as from init method, because that's where drawText method will be called from. I also need access to that same context from drawGrid method. Since we need CTX in so many different places all over the effect class, I will choose this following solution. We have CTX here on line 2. I will make sure effect class constructor expects it as an argument, and inside I will convert it to a class property called this.context. Like this. We will use this.context here and here inside the drawText method. Inside the drawGrid as well, it will no longer be expected as an argument coming from the outside. Instead, in all of these places, I will use this.context class property we just created. We also use context inside render. It will no longer expect context as an argument. I will also remove context argument past the draw method on particles and here past the drawGrid. I think I made a few mistakes here, bear with me a second please. I actually have to pass this.context to draw method on particles like this. Okay, I run the code, I get an error, I open the browser console. Effect class constructor expects CTX and converts it into this.context property. I need to make sure I pass it CTX down here on line 151 when I create an instance of that class. Also, I no longer need to pass CTX to render method here. I take drawText method and I call it from inside the render like this. When we pass x and y coordinates to fillText method, these coordinates set anchor point of that text. Where the text is drawn in relation to that anchor point depends on the value of text align and text baseline canvas properties. Text align handles horizontal alignment. We set the anchor point of the text to the middle of canvas, so look what happens when I set text align to center. I can also use text baseline property to align the text vertically in relation to those anchor point coordinates. I set it to middle. So one more time, when you draw text on canvas, the values you pass to fill text as x and y coordinates define the anchor point. Where the text sits in relation to that anchor point depends on which values you give to text align and text baseline properties. By default, the text is left aligned horizontally and alphabetic baseline vertically. We set them to center middle to get centered text like this. This is very important to understand if you ever need to work with text on HTML canvas. I will set debug to true to enable debug mode. I want this text to be visible when in debug mode. Oh, I have an error. Console is telling me it's here. I need to use this .context here as well to draw my grid. Probably you already noticed that before. So, when we are in debug mode, I want to see the vector field grid, and I want to see these big white letters that will determine the shape of the flow field. Being able to show and hide this text easily by pressing letter D on keyboard by entering the debug mode will make the effect easier to understand and modify. Inside render, I say if this.debug is true, only then draw grid and draw text. Now you can press letter D over and over to toggle debug mode on and off. Inside init method, I want to draw text at this point. Remember that init method will run just once on the first page load, and it will create vector field and particle system for us. After I draw these big white letters on canvas, I want to scan canvas for pixel data. My ultimate goal is to know which cells in the grid are over the letter shapes and which grid cells contain just a black empty background. I do it by scanning canvas for pixel data after I drew that text on it. And I will analyze that pixel data and I will map it on the grid. I will call built-in getImageData method. This method returns an auto-generated image data object representing the underlying pixel data for a specified portion of canvas. It expects 4 arguments to specify which portion of canvas we want to analyze. I want pixel data from the entire canvas element, so from coordinates 0, 0 to this.width, this.height. In other words, getImageData will scan a specific portion of canvas for pixel data. We can extract colors and coordinates of each pixel from it. To do that, I need to understand how is the data in this auto-generated image data object organized. I will assign this to a constant variable I call, for example, pixels, and I will console log it. I can see the image data object here in the console. I open it and I can see it has width and height of the scanned area. This is important. We need to know these values so that we can extract x and y coordinates of each pixel from this. If we know the width, how many pixels we have per row of data, we know after how many pixels this array breaks to another line. Canvas is scanned, and in the same order we created our angle grid, row by row from top to bottom, going left to right on each row. If I open this data array, this is where all the pixel information is stored. It's actually very simple, it just holds a long sequence of integers. My browser console splits this extremely long array into blocks, but it's actually one long line of numbers. How does that translate to pixels? I can see that this is a special type of array called UINT8 clamped array. It can only contain unsigned 8-bit integers, clamped to a range between 0 and 255. We know from RGBA color declaration in CSS that each color can be represented by a combination of red, green and blue. Each color has a value between 0 and 255, and different combinations of this allow us to create any color. In CSS RGBA color declaration, the alpha opacity value is between 0 and 1. Here, in this pixel array, alpha is also represented by a value between 0 and 255. We need to remember that. Pixel data array is an extremely long line of numbers where each 4 values represent red, green, blue and alpha of a pixel, of a single pixel. So this is pixel 1, the next 4 values are pixel 2 and so on. I can see the width of the scanned area is 528 pixels and the height is 464 pixels. 528 times 464 is 244,992 total pixels scanned, and we know that each of these pixels is represented by 4 values in pixels array. A value for red, green, blue and alpha. 244,992 times 4 is 979,968. Here we can see that the pixel data array has exactly 979,968 elements, so that checks out. If I look somewhere in the middle of the array, I should be able to find these white pixels that make up the letter shapes. Here I can see that we have 255, 255, 255, which is white, and 255 for alpha, fully visible. We know that these 4 pixels with index 533,600 in pixels data array represent pixels somewhere in this white area. If I change the fill style to red, I open the array. Mostly I see black pixels, 0, 0, 0 with 0 opacity because the background of our canvas is transparent. Here I can see those red pixels, 255 red, 0 green, 0 blue, 255 alpha. These values represent a fully visible red pixel, somewhere in the red area. We know these pixels are the text drawn on canvas. Okay, so init method will run only once on the first page load, and inside we are trying to create a grid of angles, a vector field. We drew text and we scanned canvas with that text drawn on it with built-in getImageData method. Now we are holding all pixel values inside this pixels variable. I will comment out this code, which calculated spiral angles for each cell in the grid using our special sine and cosine formula. Instead, I will make the shape of the text of the letters to determine angles held in each cell of the vector field. To do that, we need to use nested for loops again. The outer for loop will cycle over canvas row by row, jumping by cell size each time we enter a new row. We set cell size to be 20 pixels here on line 75. I can show and hide this grid made out of 20 times 20 cells by pressing letter D on my keyboard. Inside, the inner for loop will cycle through each row horizontally from left to right, also jumping from cell to cell by cell size value. Hopefully now we understand how these 2 nested for loops cycle over the canvas row by row from top to bottom. Every time we enter a new cell in the grid, we need to calculate an index. We already calculated index up here on line 40. This formula helps us to convert x and y coordinates to a single value representing index in an array. As we cycle over the grid cell by cell, row by row, I want to match that cell position with an index corresponding to these coordinates in pixel array, so that I know what pixel data was scanned for this particular cell. I'm matching x and y coordinates of the cell I am currently cycling over with these nested for loops to a specific index in pixel array to extract pixel data for this canvas area. Again, this is that formula where we multiply the row number times the width, so we get pixels per row, plus x, which represents however many pixels we are currently into a new row. This time we are trying to match index in pixel data array. We know that each particle is represented by 4 elements, 4 integers between 0 and 255 representing red, green, blue and alpha. So to get that correct index, I multiply this times 4. Now I know the index in pixels array that corresponds to the x and y coordinates of this particular cell in the vector field grid. I want the color. I start with red. Red will be pixels array at that index. Green will be the one index that comes after, so pixels index plus 1. Blue is index plus 2. Then we have alpha, index plus 3. Then we get red value of the next pixel. Green, blue, alpha, and so on and so on. So we have red, green, and blue of each pixel. Combination of these values will give us the color of the underlying pixel. Right now, all the text pixels are red, but we will change that soon. My goal now is to make the color of the letters affect the direction of the flow, the angle in the grid of the vector field. For example, red pixels push the flow to the right, blue color flows down, green color flows to the left, for example. And all the color values in between give us angles somewhere in between these directions. There are many ways I can convert colors into angles, and we can achieve many different effects here. The easiest way would be to somehow convert the three values of red, green, and blue into a single number. I can, for example, generate a grayscale value from this. RGB colors are calibrated in a way that when all three colors for red, green, and blue are equal, the resulting color is a shade of gray. The color is somewhere on the grayscale spectrum without a bias towards red, green, or blue hue. We can convert to grayscale by getting the average of all three. Red plus green plus blue divided by 3. Now I could create a grayscale effect from this by taking that average value and applying it back to red, green, and blue. But I actually just want to take that single average value and I want to convert it to an angle value. We have a range of grayscale color which goes from 0 to 255. And I want to map these values to angles between 0 and 6.28 radians. 6.28 radians converts to 360 degrees, a full circle. So colors can flow in any direction depending on the grayscale value of that area. Since we are only operating in positive values, the formula is very simple. Take the ratio between the current grayscale of this cell in the vector field and the max value, and apply that ratio to that angle value. Let's say if grayscale is 127.5, that's halfway, 50% in between the minimum value of 0 and the maximum value of 255, 127.5 divided by 255 is 0.5. We have the ratio, and now I multiply it times the maximum angle range of 6.28 radians, which will give us half of that value, 3.14. 3.14 is pi, so half circle, by the way. If grayscale is, for example, 63.75, 63.75 divided by the maximum 255 value gives us ratio of 0.25, 25% towards the max value, 1/4. We apply the same ratio to max angle value, 0.25 times 6.28 gives us 1.57 radians, half a pi, quarter circle. Basically, I'm taking the ratio, the relationship between the current grayscale value and the maximum possible color value of 255, and I'm applying that ratio to angle range between 0 and 6.28 radians. Because we used grayscale like this, the resulting flow will be influenced by how light or dark the colors are on the grayscale spectrum. I will show you what I mean when we get the animation going. I want to limit how many decimal points we get here, as there is no need to calculate tiny angle values. 2 decimal points is fine. I put the entire expression in brackets so I can call built-in JavaScript toFix method on it. I pass it 2. I want only 2 decimal points. Okay, so as the init method runs, we set flow field to an empty array. Down here, I will fill that array with a grid of angle values, built-in array push method, and we will push an object with x property set to x coordinate, horizontal coordinate from the inner for loop as we jump by cell size within each row, cell by cell. Y will be y index from the outer for loop as we jump by cell size value over canvas row by row from top to bottom. Color angle value is this grayscale color range converted to an angle value in radians, which will make sure that particles flow in a different direction over different colors. In console, we can see that image data object. I actually don't want to be pointing to the entire object, but only to the pixel array, which is held here inside the data property. So pixels will be ImageData object returned by getImageData built-in method .data. We are pointing directly to this array now. Now we see it in the console here. Flow field array now contains objects with X, Y, and color angle properties for each cell in the vector field grid. We need to make sure we account for this change when updating particle positions. Up here, inside update method on particle class. Here, we are pulling angle value from flow field array depending on particle's current X and Y position on canvas. Now, there is an object with 3 properties at each index, so I need to access its color angle property here. Like this. Nice. Something is happening. We have 2 problems to solve. I only want to run this code block that matches particle position to an object representing a cell in the flow field if there is an object at that index. Only then pull the color angle. That will fix the issue where particles move outside the bounds of canvas between resets. The second issue, if you are coding along, you can zoom out and you can see we are already drawing a flow field shaped as letters JS, but for some reason it's skewed to the right. Why is that? I will make the font smaller so we can see. We have the shape, but why is it distorted like this? I make the cells smaller. Now we can clearly see the flow field is shaped as letters JS, but it's skewed in a strange way. It actually took me a few minutes to realize what's going on, but let's fast forward to the solution. If you know why it's doing that before I reveal it, pause the video and type it in the comments right now. You see? Up here, we are setting canvas width and height to the current width and height of the browser window. The problem is that when we create the flow field, if cell size value on the main effect class, the width and height of each cell in the grid is not a number that canvas width can be divided by without any remainder, we will get some leftover pixels when we break line as we scan canvas row by row from top to bottom. As we go down row by row, those leftover pixels at the end of each row accumulate to the flow field grid. And the flow field grid, the number of elements in there, doesn't exactly match the number of cells we can fit on canvas, so the rows get pushed more and more to the right. There are multiple ways to solve this. We just need to make sure that canvas width is divisible by cell size without any remainder, without any leftover values. I will solve it by setting canvas width to a specific size, but you can also use a dynamic formula here using the remainder operator if you want to keep it full screen, if you want to keep the responsive functionality. I set canvas width to 600 pixels, and because cell size on line 75 is set to 20 pixels, 600 is divisible by 20 without any remainder, so we are getting the correct shape. I will also set canvas height to 600 pixels, or maybe 500 times 500. When I resize canvas, our custom resize method gets triggered and it breaks the shape, again because it allows canvas width to be something that is not directly divisible by cell size without any remainder. I can either make sure it only resets canvas size if the new width is divisible by cell size, or I can just comment it out for now down here on line 92. And because canvas is 500 times 500 pixels, I want it to be centered exactly in the middle of the page. I can do that with CSS. It has position absolute already, so I give it top 50%, left 50%, and transform translate minus 50%, minus 50%. Of course, you can position it in a different way depending on where you want it. I will now just set the background on the body element to black. I think this looks alright for now. I increase the font size. 450 maybe? Yeah. We are converting color to an angle, so look where the particles are flowing when the text is red. And look what happens to their direction of movement when I change the color to green. Blue angle is actually similar to red. It's because we are not spreading the color range itself, but we are converting it to grayscale first, and then we are converting that to angle. It seems like blue and red have a very similar grayscale value. You will see the biggest difference in angles when using colors that are light or dark, colors that are far apart on the grayscale spectrum. Brown. Let's try something much lighter. Yellow. We can clearly see that direction of the flow is influenced by the color, by the text color. Perfect. I could leave it here, but I was playing with it and I came up with more really cool things I want to share with you. This is always my favorite part, where we have all the logic in place, the effect is running, and I can experiment. We know that different colors push the particle flow in different directions, so let's see what happens when the fill of the text is not just one color, but a gradient that transitions from color to color. I wonder what that will look like. A custom variable called gradient1, and I call built-in Canvas create linear gradient method. It expects 4 arguments, x and y of the start point and x and y of the end point. Gradient will be drawn along a line between these 2 points. I want a gradient from top left corner, coordinates 0, 0, towards the bottom right corner coordinates, effect width and effect height, which are the same as width and height of the canvas. Now I can take that gradient1 variable and I call built-in addColorStop method from it. At offset 0.2, the color will be white, for example. 0.8 offset, I try full blue. Now I can just set fill style to this gradient1 variable. Awesome, this is so cool. Look how the flow curves as we go from blue to white. Now that we understand this, we can experiment with different color ranges and different gradients. I add another color stop at 0.4, yellow color. .6 will be, for example, green. I can just play with the color values to see what flow I get. It's interesting how the flow direction changes as the colors transition following the gradient. I forgot to mention one important feature of fill text and stroke text built in Canvas methods. We can pass them optional 5th argument to define max width of the text. I will say that max width of the text is the width of Canvas. Now, if the text is longer, it will be squished to fit into the area. If I want some margins, I can say this.width times 0.8 and the text will take the maximum of 80% of Canvas. It will take 80% if we give it more space by setting Canvas width to a larger value. I go back to canvas size 500 times 500 pixels. I change the word to flow. We can change font to Helvetica, for example. Back to impact. And text will be JS. I want the flow to curve more to the right, so I play with the color values to get the gradient influence the direction of the flow field. This looks nice. I copy this code block and I rename all of this gradient to, and I use that as fill style on line 112. I play with the values again to see what happens. I roughly know which direction each color flows, but it's mostly trial and error. This looks interesting. I create gradient 3 by copying this code block and using that as fill style on line 118. This time it will be a radial gradient, so we need to pass it 6 arguments. X and Y of the center point of the inner circle and its radius, so I want the inner circle to start exactly in the middle of canvas horizontally and vertically, and radius will be 10 pixels. The outer edge of the radial gradient circle will be again from the middle of canvas, and radius will be this.width. Interesting. I adjust the colors to see what shape I get. You can see how the radial gradient affects the flow in a different way. I really like this one. I will keep all 3 gradients I defined so I can swap between them later if I want to. When angles change direction, it's a sharp turn. It might work for you, but maybe we want the lines to turn more gradually when the angle in the vector field changes. We are holding the current angle value for each particle here on the main particle class. We are changing this value inside update method to match the angle value of the grid in the flow field. I will create another property here called new angle, and I will check the difference between the current angle and the new angle. And instead of changing to that new angle instantly when particles enter a new cell in the flow field grid, we will just push particles towards that new angle by a certain fraction of their difference. Or, to reduce the calculations needed, rather than calculating the fraction of the difference between existing angle and the new angle, I can just have a set value called angle corrector. It will be a small value in radians. Down here in the update method, I set new angle to an angle stored in the cell of the vector field. And I say if the current angle of the particle is more than new angle, reduce the angle value of the particle by the angle corrector value we defined. Move the existing angle one step closer to the new angle. I choose to do it this way to save performance. You can also say change angle value by 1/10 of the difference between angle and new angle, which will give you more gradual curves at the expense of performance because more calculations are required. Else if angle is less than new angle, increase angle value by angle corrector. One more else where we set angle to new angle. Now you can see the sharp turns are gone and we are just gently pushing the particles towards certain angle values. I adjust angle corrector value to push them a bit harder. Or we can do a random value here between some small range, so that each particle curves differently. I can adjust max length. I can change speed modifier. We have all the logic in place. If you want, you can play with it to see what variations of this effect you can come up with. So this is my very basic performance efficient way how to make particles change directions more gradually as they flow over the grid of cells in the flow field. I would also like to be able to control how many particles flow inside the letter shapes and how many flow in the area outside the letters. Now it's completely random, but it doesn't have to be. When the particles reset, I wanted to check if it's resetting within the letter shapes or outside of it, somewhere in the transparent area around the letter. If it's outside the letters, I wanted to try again. I will have a variable called attempts. It will start at 0 at first. I will have a flag called reset success. Initially it will be false. When the particles reset inside the letter shapes, we will switch this to true. I will have a while loop. When the particles reset, I want it to try 5 times. It will make 5 attempts at randomly picking a position somewhere in canvas to try to reset within the letter shapes. As long as attempts are less than 5, and as long as reset success is false, I will create a test index. It will be a random cell somewhere in the flow field array. I check if this test index has alpha more than 0, which would mean that it's the cell in the flow field that has some visible color in its pixel data, which would mean it's one of the letters. Alternatively, it would be transparent, which would mean it's the empty background around the letters. If it has alpha more than 0, it means we found one of the letter cells, so we set x and y positions of the particle to x and y positions of the cell in the flow field grid. Down here I can see that flow field cells Objects inside flow field array contain x, y, and color angle values. So this x and y will be coming from there. I set those x and y coordinates as the first point in the path by adding it to the history array, and I reset timer back to max length times 2. I will also set reset success to true. Importantly, I need to make sure every time we try to do this, we increase attempts by 1, so that when we reach 5, this while loop ends. We don't want to create an endless while loop. It will continue only as long as both of these conditions are true, so only when attempts are less than 5, and at the same time as long as reset success is false. If I run the code, it doesn't reset at all, so that indicates this condition on line 78 is always returning false. It's because we are not pushing this alpha value into our flow field cell objects. I changed attempts up here to 50. So down here I'm calculating alpha on line 160. I need to make sure that the value actually ends up inside flow field array, like this. Perfect. Lines are resetting inside the letters. I set max attempts back to 4. After the while loop has finished, if after trying to reset 4 times we still haven't found a cell with alpha more than 0 and reset success is still false, we will restart x and y coordinates of that particle somewhere randomly around the canvas. It's still not resetting particles outside letter shapes even when I go down to just 2 attempts. How about only 1 attempt? I will figure this out, just give me a second. Right, I have to put these new positions inside history array, and most importantly, I have to reset timer back to max length times 2 for the particles to animate. Nice, so now when particles reset, this code will attempt a certain amount of times to reset the particles inside the letter shapes, and if it doesn't find the cell in the certain amount of attempts, it will just reset the particle somewhere randomly around canvas. We can tweak how many particles we want to reset inside and outside letter shapes by changing the number of attempts on line 75. The less attempts, the less likely particles are to find the letter shapes in time, so they might reset outside. I can increase the number of particles, and I increase the cell size. We can see most particles now reset within letter shapes, but occasionally we get one resetting somewhere else, somewhere outside. You can adjust the number of particles and cell size to whatever you want, and whatever your computer can handle here. I can remove this code. I think we all now understand how these values affect the animation. Maybe 2000 particles. What if I add white color to the colors array for some highlights? Interesting. I remove it again. I try gradient 1 to change the direction of the flow field. Gradient 2. I think my favorite is gradient 3. Which one do you prefer? I increase max length, which does have effect on performance. Longer lines take more computing power to draw. So we create a grade, we draw text on canvas, we analyze that canvas with text drawn on it for pixel data. We cycle over that pixel data in a grid to extract color values and coordinates of each pixel, and we convert these resulting colors into angles. From that information, we create a flow field, a grid of angles, where the direction of angles is influenced by the text that was drawn on canvas. I can remove this code block. Then we create a particle system here. Maybe I want the particles to start flowing from the letter shapes even on the first page load, so I will manually trigger reset method on each particle as I create them, which will force them to make a few attempts to find cells in the flow field that contain some color values, cells that are over the letter shapes. I change the text to flow. You can see that it messes with the radial gradient, which is expected. I increase canvas width to 1500 pixels. I can create max width of the text down here. I can use gradient 2 to change the flow direction. This looks interesting. How about gradient 1? You probably realized that this would work on images as well, as I'm just using getImageData to get shapes of letters that were drawn on canvas. In the extended version, I will show you step by step how to do this with images. We will learn how to preserve the original colors of the image and how to animate between color transitions, which I haven't done here yet. Extended version also includes multiple source code downloads from different steps as we progress through the projects, and I also include some bonus experimental flow field code bases. Check out the links in the video description. Thank you to everyone who supported me by buying some of my premium extended classes on Udemy or Skillshare, and if you don't have money, don't worry, I will always release a lot of free content for everyone here as well. Click the like if you found some value today, and thank you for coding with me. See you later.